Sleep medicine centers on the objective of thermoneutrality. Thermoneutrality is the specific range of ambient temperatures where an organism maintains its core temperature without needing to increase its metabolic rate. While clinicians measure the room, the determinant of sleep quality is the microclimate, the thermal boundary layer trapped between your skin and the mattress. Standard sleep environments attempt to maintain this balance through constant temperature control, or CTC. This usually involves setting a mattress pad or heated blanket to a static 33 degrees Celsius, the recognized temperature for skin comfort. A microclimate fixed at 33 degrees Celsius feels comfortable at the start of the night, but this approach assumes that the human body requires the exact same thermal conditions from sleep onset through every subsequent stage until morning. New polysomnographic data suggests this logic is flawed. Polysomnography is a comprehensive sleep study that records brain waves, oxygen levels, and heart rate during rest. This data shows that a static thermal environment actually fragments late-stage sleep and lowers overall sleep efficiency. Human sleep physiology is a dynamic process, not a static one. Attempting to force the body into a single, unchanging thermal environment creates a physiological mismatch that degrades the structural integrity of sleep. This chart from a 2025 study by Kim and colleagues details a 3-arm crossover trial involving 25 participants. The researchers used this design to directly compare how different mattress temperatures affected the same individuals across multiple nights. They compared 3 specific conditions: natural sleep without intervention, a 33-degree constant temperature control, and a novel protocol called real-time temperature adjustment, or RTA. The dynamic RTA protocol significantly increased average total sleep time to 383.2 minutes. Sleep efficiency also improved, reaching 87.3%. Crucially, wake after sleep onset, time spent awake after falling asleep, was successfully suppressed by RTA, actively reducing sleep fragmentation compared to static mattresses. This data indicates that an actively changing microclimate improves every major sleep metric compared to even the most calibrated static environment. To understand why these changes matter, we must look at how the body enters NREM sleep. We seek skim-level warmth, curling up or using blankets, to trigger vasodilation. Vasodilation is the widening of blood vessels, allowing the body to transfer heat from the core to the skin for release. Sensory channels in the skin detect this warm 33-degree microclimate. Specifically, TRPM2 receptors act as thermal sensors. TRPM2 is a protein-coding gene that forms a channel sensitive to shifts in environmental temperature. When these receptors detect warmth, they send a neural signal up the spinal cord to the lateral parabrachial nucleus in the brainstem. From there, the signal terminates in the median and medial preoptic nuclei, or the MNPO and MPO, located in the hypothalamus. This signal activates glutamate and NOS1 neurons within the MNPO. These specific cells have a dual role. They induce NREM sleep and simultaneously trigger core body hypothermia. This in-warmth maintains the peripheral vasodilation needed to dump core heat. This process lowers the temperature of the brain, which is a physical requirement for maintaining deep NREM sleep stages. Maintaining this 33-degree microclimate triggers the preoptic hypothalamus, providing the specific thermal signal required to initiate NREM sleep. The body's requirements shift when it moves from deep NREM into REM sleep. REM, or rapid eye movement sleep, is the specific stage associated with extremely high brain activity and intense dreaming. During REM sleep, the body's homeothermic thermoregulation is suspended. This means the sleeper temporarily becomes poikilothermic, effectively cold-blooded, and loses the ability to sweat or shiver to regulate temperature. In this state, a static 33-degree mattress becomes a threat. Because the body cannot actively cool itself, the heat from the mattress begins to accumulate in the sleeper's tissue. To prevent heat stress, the brain is forced to abort the REM cycle. This triggers a microarousal, waking the individual just enough to change their thermal state. The Kim study explains why the constant 33-degree mattress failed. That persistent heat trapped the defenseless body, forcing the brain to repeatedly interrupt sleep to prevent overheating. A fixed thermal environment creates a conflict for the brain during REM sleep, trapping it between the need for restorative rest and the necessity of preventing heat stress. The real-time temperature adjustment algorithm acts as an engineering solution to this conflict.
This protocol aims to optimize REM latency, which is the amount of time it takes to reach the first REM cycle after falling asleep. During NREM sleep, the AI uses sound detection to verify the sleep stage and holds the mattress at the 33 degrees needed to keep the NREM-promoting neurons active in the hypothalamus. The algorithm intervenes the moment REM is detected. It drops the mattress microclimate by 3 degrees, down to 30 degrees Celsius. This drop functions as an external autonomic prosthesis. By cooling the microclimate, the mattress artificially regulates the sleeper's temperature, precisely when the body's internal systems are offline. 30 minutes before waking, the mattress temperature increases to 36 degrees. This mimics the body's natural circadian temperature rise, which helps reduce sleep inertia and facilitates a smoother transition to wakefulness. This chart shows the impact on REM latency. By protecting the REM cycle from heat-induced disruption, the RTA protocol allowed subjects to enter REM sleep 31 minutes faster than the control group. By mechanically compensating for the body's suspended thermoregulation, the RTA protocol prevents environmental disruption and allows for more consolidated sleep cycles. Trial data further showed that the architectural improvements from this thermal intervention varied significantly based on biological sex. Men responded to dynamic adjustments with a significant increase in REM sleep, reaching 21.3% of total sleep time. Women experienced a different shift. Their deep sleep percentage nearly doubled, rising from a 7.1 baseline to 12.3% under RTA. This difference is likely due to the distinct ways estrogen and progesterone influence baseline thermoregulation. These hormonal balances change how different bodies utilize the external cooling provided by the mattress.
By adjusting to these baseline differences, adaptive microclimates stabilize restorative processes that static environments actively disrupt. Treating the sleep environment as a static room setting is a practice based on incomplete assumptions about human physiology. Sleep is a volatile biological oscillation between active thermal management and total thermal vulnerability. Progress in somnology depends on viewing the sleep environment as a responsive, AI-driven medical device. Somnology is the scientific study of sleep and the diagnosis and treatment of sleep disorders. By synchronizing a microclimate to the shifting demands of the brain, we move past simple comfort. We provide the specific thermal conditions necessary for a mathematically superior night of rest.